This is part 2 of section 10.1 sequences. In this part, we're going to look at more ways to determine if sequences converge and diverge, and we're going to talk about a very specific type of convergence sequence, which is a bounded monotonic one. So let's start by looking at ones when we do the limit. This will be a nice review that we may have to use L'Hopital's rule to determine whether the sequence converges or diverges. So example 6, letter A, what we're going to do is we want to take the limit as n approaches infinity of n over 2n minus 2. And if we were to do this, we would end up with infinity over infinity. So we need to use L'Hopital's rule. And when we do that, what we're looking at then is the limit as n approaches infinity of 1 over, so the derivative of n is 1, and the derivative of 2 to the n minus 2, the minus 2, that'll be 0. 2 to the n's derivative is 2 to the n times the natural log of 2. So now when we take the limit of this, what we get is that looks like our 1 over 2 to the n sequence. So this is going to converge to 0. Now, we're asked to use L'Hopital's for the next one, but if you use your rule of horizontal asymptotes, you already know what the answer is going to be. It's going to be 3/2. But just in case you have to show your work for it, you want to make sure you're going through the steps of L'Hopital's rule. And in this case, we're going to have to do it twice. So, because they're both to the second degree. So the limit as n approaches infinity of 3n squared minus n plus 2 over 2n squared minus 1, this is going to approach again infinity over infinity. So we're going to use L'Hopital's rule. And when we do that, we're going to have the limit as n approaches infinity of 6n minus 1 over 4n. And again, we're still having infinity over infinity. So we're going to use L'Hopital's rule again. So this time, we're now going to take the limit as n approaches infinity of a constant, 6 over 4, and that is, of course, 6 over 4, which is 3/2. So this sequence, of course, converges, since our L is a real number. Okay, now finally, we're going to talk about a very specific type of convergence sequence, which is a bounded monotonic sequence. So you may not be able to find the actual limit, but you still can tell if it converges. So this is a theorem that can be very helpful. So we can say if a sequence a sub n is bounded and monotonic, then it converges. So bounded from before means there is a limiting value to the function, but monotonic means that its terms are non-decreasing or non-increasing, not both. So in other words, if they're non-decreasing, that means as n gets larger, each a sub n is either the same value or larger than the previous a sub n. And if it's monotonically decreasing or non-increasing, a larger n will produce the same value or a smaller a sub n than the previous one. So now we're going to give the definition of a bounded sequence. So a sequence is bounded above by a real number m if m is greater than every term in the sequence. And a sequence is bounded below by a real number n if n is less than every term in the sequence. So then we can say that a sequence is bounded if it's bounded above or below. So if it's bounded, and we can also say it's monotonic, then we know it converges without actually finding the limit of that sequence. All right, looking at example 7, we're supposed to determine if it's bounded, monotonic, and convergent. So here's our sequence, and what we're going to notice is it is definitely decreasing. And with that in mind, we'll notice that it is indeed monotonic. Because as n is increasing, a sub n is going to be less than a sub n minus 1. Okay, the values are definitely going down. We can also say it is bounded below, because it does have a limiting value below. And we can see here it's bounded below by 0. Since those two conditions are met, this sequence converges. And it's going to converge to 0. Next, we have kind of the opposite here. This time, what we have is we have a limiting value on the top. So this sequence is bounded above. We can also say that it's monotonic because each previous a sub n is less than the one after it. So they keep going up. They never come back down again. Since it's bounded above and monotonic, this sequence converges. And it's going to converge to, it looks like, 6. Our last two examples. For this one, what we can see is that this is indeed bounded. This is a bounded sequence. It's bounded above and below. Because we could pick a number above and below our smallest and largest values and bound it. But it is oscillating because it is not monotonic. The values do not follow that pattern. Here it starts out that they're getting smaller, but then a sub 3 is bigger than a sub 2 after we were decreasing. So we keep increasing at a sub 4, but then we start going down again. So this is not monotonic. So this sequence diverges. And then finally our last one, it is monotonic because we can see that a sub n minus 1 is definitely less than a sub n, but it is not bounded. It's going to increase without bound. So we would say that this sequence also diverges. Okay, that is our end of our lesson on sequences. So we are going to use these concepts in the next couple of sections to start developing an idea of tests for convergence and divergence. And we're going to bring along with that the idea of an infinite series. So these concepts will be coming into play in all our subsequent sections. So if you have any questions, as always, you can ask them in class.